To model the at most 2 colors in each slab for the steel mill slab problem, we needed logical constraint of this type. We needed a constraint is or, so that the variable b is true if and only if the disjunction there is true, which means that there is at least one of the variable there in the or that is set to true. How do we model that constraint, that is or constraint? How do we implement it in terms of propagator? This will be the filtering rules that we'll use. So, assuming that b is detected as to become true, this variable becomes true. In that case, you can simply post here the disjunction constraint. If b is set to false, it means that none of them can be true, which means that you should set all of them to false. Now, if one of the xi becomes true, then you can set b to true and deactivate the constraint. And when you detect that all the variables there are false, you can also set b to false. This way you have propagated in every possible directions of this is or constraint. Now I will explain how to implement here the or constraint, because in case b is true, you will post the or constraint. So the or constraint wants that at least one of the variable is true. The question that you should ask yourself is, in which situation can you possibly propagate and do some detections? The only thing that you can do in terms of propagation there is when all the variables are false except one. When you detect that only one variable is still not false, it can still be true or false, then you should set that one to true, because you need that at least one of them is true. And since it's the last one, you should set it to true. We call that unit propagation, and it's the type of propagation that is done in modern SAT solvers. So one first implementation to make it a little bit more efficient than instead of going through every variable at every call to the propagate method is to use the technique of sparse sets. You can split the sparse set between the variables that are fixed, the variables that are not fixed. When one of them becomes fixed to true, you can deactivate the constraint. And then if you detect that the set if the sparse set becomes empty and all the other variables are false, then you can simply detect a failure and backtrack. And when one of the variables is not fixed and the other one are set to false, then you can set the last one to true. That's the unit propagation. So it means that on average, it will take constant time per variable. But in practice, we can do even better than this. And the technique is what we call the watch literal techniques. The idea is that we will not listen to the changes of all the variables involved, of all the Boolean variables involved in the OR constraint. We will simply listen to two variables. Okay, we will call that the watch left and the watch right. And these are not fixed variables. The other one, we assume that all the one on the left are already decided to false, and all the one to the right of WR are also set to false. But these ones are not yet fixed. Okay, and so we are only interested by the changes of these two variables. Okay, if we detect that one of them becomes true or false, then we can possibly act. As you can see, this constraint is already satisfied because in the middle of it, we have a 1, which means that there is at least one Boolean variable that is true, and so the constraint is already satisfied. But the propagator doesn't know it. It doesn't know it because it's only listening to this one and this one. So now assume that this one is fixed to 0. So in the next propagate call, what you will do is that you need to update this pointer to the watch literal of the right. And so you will move one to the left, and you will now listen to this one. Okay. So now you will listen to that one, and you will dynamically say that you are interested to be notified on every change on the domain of the variable x6. And again, the constraint is already satisfied, but we do not know it yet. Okay, but that doesn't matter, right? Because we do not fail, and we have a very cheap here. We have a very cheap footprint on the fixed point because we have only here two variables that we are interested to listen to. And so, and now we register. We say that we are interested to be notified on the changes of this variable x6. Okay, so you will move the 2 pointers to the left. Okay, if you detect that the 2 pointers are pointing to the same variable, it means that it's the last one. Okay, that's the last variable. So since it's the last one, that corresponds to the unit propagation case, and so we can simply set that variable to 1. Okay, if we cross the 2 pointers, okay, it means that all the variables are 0. In that case, we must fail because the OR constraint asks that at least one variable is true, and that's not the case. So there is the detection of an inconsistency in that case. And so again, this OR constraint will be dynamically posted by the is OR constraint. If we detect that B is true, then we can post this constraint, and we can use the watch literal technique to make it very, very cheap to propagate. That's it for the steel mill slab problem, and you will implement all the ingredients to solve that problem. 38 of the TSP, so the steel mill slab problem: the bin packing, the symmetric breaking constraint, the logical constraints.